All right, here we are, another happy Monday morning. So we have a lot to do today, a lot of fun stuff as well. And let me go get Moodle open. Wait a minute. This is not what I wanted. Oh, here we go. Okay. All right, so first I have to log in. So basically where we left off with was we were part of the way through chapter 5C. Okay, so let me get that open. If I remember correctly, we saved one last topic. Okay, yes, that last topic was sequences we hadn't quite gotten to, but it just suddenly dawned on me. I almost completely forgot. I think today we're supposed to go over the chapter 5 problem set number 1. Okay, there it is. Okay, I almost forgot. Yes, so there's 3 of them. And because you should have no trouble with this one, I think we should do this one today. And then we'll do the second one on Thursday. And then by that time, we'll be completely done with chapter 5. So we might as well do the third one next Monday. This way you've got time to work on them. Some of these are fairly time consuming. Not so much this one. This is fairly easy, but oh, okay. All right. Thank you. Yeah, I know the internet just is not that reliable. I mean, almost without fail, when I started up a new session, somebody's having trouble getting in, almost without fail. So I'm glad you told me though. Thank you. So yeah, it happens. You know, it happens a lot for some reason. So, but anyway, so yes, so chapter 5C is here, and so yes, we've been looking at the properties of the real numbers. We did all kinds of fun stuff with exponents. And of course, we went through scientific notation. And I believe we left off with sequences. Yes. Okay. That would be the last topic of chapter 5. So with that to look forward to today, we need to go over the problems in chapter 5, problem set number 1. And then we may start chapter 6 today. We'll see how that goes. And then we also have, as usual, some fun videos that we will look at as soon as we're done with chapter 5. Now, it looks like we are ready for, oh, okay. So we've already seen, last time we saw the Pythagorean theorem and the band numbers. So this time we want to look at this infinite hotel paradox. It's quite an interesting video. It's all about infinities. And you might think infinity is just a single concept, but it's actually it's much more complex than you might think at first. And so this video does, in a very excellent way, explain to you all the different features of infinity that you might not have known about. And then, of course, we never get tired of talking about prime numbers, do we? So we'll have that. And we'll save quadratic equations maybe for next time. So yeah, I mean, there's no shortage these days of excellent math videos. I think you'll agree that it's fun to see how this stuff came about and how it can be applied in the real world. So we'll do that whenever possible. All right, anyway, so number 1 priority right now is to get to these solutions. And I think you'll realize as we go along that, you know, this is exactly what we've been doing and you shouldn't have too much difficulty with it. And that's good. If you are able to do these questions, the problem sets, then most likely you'll do very, very well on the actual exams because they'll be very similar to this. Okay, so let me just quickly save this. 1 second. Okay. So this is chapter 5. Okay, and today's the 20th. All right, let's see how this goes. So we start with 16. So what pairs of natural numbers give us a product of 16? Well, we have 1 and 16, We have 2 and 8, and we have 4 and 4. Are there any others? No. Okay, so in other words, if I continue to go down the list, eventually I would reach 8. I don't need to separately write 8 and 2 because it's already there. Now, if you want to, at the end, what we often do is we write up a complete list of these. In other words, you could say that these numbers are the factors of 16. And the reason for that is because each one of them evenly divides into 16. Okay, in other words, if I divide 16 by any of those numbers, whatever number I get, whatever remainder I get, whatever result I get, there will be no remainder. Okay, that's what this is all about. So 16, for example, divided by 8 is just 2. 16 divided by 4 is 4, et cetera, et cetera. So as long as you can divide by that number without there being a remainder, then you have a factor. Now, some of these are going to be trickier than others. Some of these have a surprisingly large number of factors. And there are tricks and tips that you can use to help you decide which ones might be factors. For example, even numbers. Clearly, this is not an even number. So therefore, we cannot divide by 2. But what about 3? Well, you might say to yourself, well, let me get out my calculator and see if 3 divides evenly into that. And the answer is yes. But there's a trickier, clever way of deciding this. And this is, let me just put this in here in parentheses. This is a little fun fact. If the sum of the digits in a number is a multiple of 3, then the number can be divided by 3. Okay, in other words, in this case, 2 plus 2 plus 5 equals 9. Since 9 is a multiple of 3, this guarantees that we can divide, or that 3 divides evenly into 225. In other words, dividing 225 by 3 will result in a remainder of 0. And in fact, 225 over 3 does equal 75. So there's no remainder. So in other words, you can spot that right away. If you added up those digits and you said 2 plus 2 plus 5, what is that? 9. Oh, that's a multiple of 3. That means I can divide 225 by 3. 3, therefore, is a factor of this. And it always works. There's no number for which this fails to work. So just remember that 3 is a nice, easy one because you just add up those digits. There actually, in principle, are rules for all of the first 10 digits. But some of them are so complicated that I don't think it's worth your while to try to remember them. But certain ones are very obvious. For example, if the number ends in 5 or 0, you might recall, then it must be divisible by 5. Therefore, 5 is one of its factors. And that's the case here. So we run into another one of our rules. If a number ends with a 0 or a 5, then the number can be divided by 5. Okay, and so here we have 5 times 25. Wait a minute, sorry, not 5 times 25. If you divide that by 5, you'll get 45. Okay. All right. Sorry, 545. Now, we didn't bother with 4. Why didn't I try 4? Because this is not an even number. It's not going to work. 6, it doesn't look like it. How about 7? You never know with 7s. Now, if you're not sure, just go to your calculator and divide. No, not this time. How about 8? No, it doesn't look right. No, because 8's an even number. 9 is a possibility, though. Oh, how interesting. 925. That worked out rather well. And then how about 10? No, that's not going to work. 11? No. 12? Wait a minute. 15. This happens to be 15 squared. In fact, it is one of our perfect squares. If you didn't recognize it, 225 is 15 squared. So now we're done. So we can gather them up and we say that the factors of 225 are 1, 3, 5, 9, 15, 25, 45, 75, and 225. Wow, that's a lot of factors. For such a small number, that is kind of a lot of factors. So I'm just double checking to make sure we didn't miss any. Nope, they're all good. All right, what about 126? Well, right off the bat, we know we start with 120. By the way, these are not, it says factors. It doesn't necessarily mean prime factors. Prime factors would exclude the 1, but these are just all the factors. Now, this is an even number, so we're guaranteed that it's divisible by 2. How about the 3? Remember that rule for 126, 1 plus 2 plus 6 equals 9. And again, which is a multiple of 3. So this number is divisible by 3. Therefore, it is a factor. So 3 goes into this 42 times. How about 4? Now, it looks like it might work, but if you do the division, it turns out no. Now, you know it's not 5 because the last number is not a 5 or a 0. Could it be a 6, though? Why, yes, it is. 6 times 21. 7 doesn't look right. It doesn't have that look to it. 126 divided by 7. But, oh my God, I spoke too soon. Look what happened. 7, I don't know, it just didn't look right. And all of a sudden you divide and it turns out 126 divided by 7 is in fact 18. So there you go. You never know. 128, no, it doesn't work. How about 9? That might be a possibility. Yes, 9 times 14. Okay, wow. How about 10? No, you can see it doesn't end in a 0. 11, no, it doesn't look right. 12, 13. No, it looks like we're done then, because the next one would be 14, which we already have. So therefore, the factors of 126 are, we can list them all out, 1, 2, 3, 6, 7, 9, 14, 18, 21, 42, 63, and 126. So realistically, with these factors, the biggest challenge is to avoid missing any of them. In other words, you're not likely to write down ones that are wrong because you can easily check them, but it's possible you could overlook one. So that's what you want to keep your eyes on. Is this correct? I mean, am I missing something or not? And if you're not sure, just go through and divide by every number from 1 to 10. 1 to 9, well, 1 to 10 should be helpful. All right, one more, 1 and 54. Now this is an even number, it must divide by 2. And watch this. What do you know? Since 9 is a multiple of 3, 54 must be divisible by 3, which means you got 3 and 18. 4, no. 5, no. 6, no. 7, 8. No, well, this one is surprisingly low on fact. Oh, wait, no, sorry, missed one. 6 times 9, sorry. Then 7, no. 8, no. 9. All right, and then we're done. Okay, so the factors of 54 are 1, 2, 3, 6, 9, 18, 27, 54. Now, that's still a fairly good number of factors. But, you do get numbers that don't have a lot of factors. And of course, we know that with prime numbers, you're only going to get one in the number itself. All right. Now, what about the multiples? The multiples are easy because literally all you're doing is multiplying this by the first 5 natural numbers. Okay, so the first 5 multiples are 3, 6, 9, 12, and 15. Yeah, these are easy. 7, 14, 21, 28, 35. And again, just notice all I'm doing is multiplying that number by 1, followed by 2, followed by 3, followed by 4, and followed by 5. Very good. And then, oh God, 10 is the easiest one of them all. Right, you could do these in your sleep: 10, 20, 30, 40, and 50. I mean, some of these are messy, but yeah, most of these you could probably do in your head: 12, 24, 36, 48, 60. And then finally, 15, 30, 45, 60, and 75. Okay, now the prime factors. Now, remember, this is the case where we do not want to include the 2. I'm sorry, the 1. We do want to, just not 1. Now, remember, we came up with this wonderful graphical technique for doing this, which I think we should continue to use because it's so useful. So for example, let's start with 16. Remember, we're creating what's called a binary tree, which basically just means that it has 2 branches at every step. And those branches represent prime, well, they represent factors. When we're done, we'll be left with just prime factors. That's the goal. All right, so yes, we start out with just any factors we choose. We don't have to pick any particular, go in any particular order. In other words, I'm going to take 16 and break it up into 2 times 8. Now, since 8 is not prime, we're not done. This becomes 2 times 4. And since 4 is not prime, 4 is not prime, so we're not done. Okay, but now we're done because all we have at the bottom here are 2's, which are all prime numbers. So the prime factorization, well, you know, you could probably leave it like this, but you could also write that the prime factors, or I have a better idea. The prime factors, I guess you could write it like this. You don't see it done this way usually. Normally what we do instead is we write the prime factorization is 2 times 2 times 2 times 2. They both mean the same thing, of course. All right, you could do either one. Okay. All right, 18. What do we do with that one? This will be quick. You'll see why in a second. 2, 9. Okay, we're done. Look how easy that was. Okay, if only they were all that simple. So if you could write this in one of 2 equivalent ways. The prime factors are 2, 3, 3, which means that the prime factorization is 2 times 3 times 3, because of course that equals 18. All right. And by the way, if you started with something different, like 3 times 6, you would still eventually get the same result. In other words, let me show you that to you right now. The order, like I said, doesn't make any real difference. If you'd started with 3 times 6, not a problem, because you're still getting the same 3 factors. Any way you look at it. So the order in which you do this is irrelevant. All right. All right, what about 1296? That one might take a while. That's a big number. And since it's even, we'll start with 2. Even again. Even again. Even again. Now we're getting somewhere. Oh boy. Sometimes you have to be careful with these trees that you don't run out of space. Let's do 9 times 9, let's say. Man, that's a lot of factors. So you've got so we'll put 2, 2, 2, 2. So there's 4 2s and there's 4 3s. Okay. Usually we try to write them in order. In other words, you notice how I've got all the 2's and then all the 3's. The normal convention is to have all the smaller prime factors first. It's just easier to keep track of them. It's like anything else. The neater, let's say your desk is, the easier it is to find things. It's just really just that simple. All right, so you know what I mean. Or the better organized your closet is, the easier it'll be to find that particular shirt you're looking for. Okay, and of course we could also say that the prime factorization 1296 is 2, 2, 2, 2, 3, 3, 3, 3. And you can double check that that does in fact give us back 1296. And you don't have to go nuts typing in all these numbers. You could actually rewrite this if you really want to. You could write this as 2. When you start getting a lot of repetitions, you're more likely to run into this. Because of course it means the same thing. Now, 1960, oh my God, we're going to have tons of factors for that one. In fact, I'm going to move this to a new page. I do not want to run out of room. Oh, you know what? I guess maybe I didn't say this, but when we're done here, I'm going to copy this into Moodle, this whole document, which has all my handwritten notes here. So that if you miss something, you'll have a copy of it. Okay, very good. You never know. You know what happens if the phone rings or something right in the middle of this? You never know. So we have the recordings, but you'll also have this document. All right, so once again, we've got evens all over the place here. Yes, lots of even numbers. But now things take a turn. This one, if you add up those those digits, you'll get a 9, which is a multiple of 3, which means, oh wait, sorry, no, you don't. My fault. I added wrong. All right, so instead, we're going to have to try other possibilities here. All right, so 245, what goes into 245? I have a feeling that 9, let me try 9. No. Five. What am I doing? 5. Of course, 5. It ends with a 5. It has to have 5. There we go. Now we're getting somewhere because clearly 49 is a perfect square. And therefore this is 7 and 7. Now these are all prime numbers. Okay, so the prime factors are 2, 2, 2, 5, 7, 7. Prime factorization is 2 times 2 times 2 times 5 times 7 times 7. Okay, well that was a little challenging because of that 245 sitting in there. Yeah, but remember, since it ends with a 5, you're guaranteed that it's divisible by 5. Otherwise, just take your calculator out and just run through a bunch of possibilities until you find one. Okay. So far, so good. Oh, did I miss something? There we go. Yes, sorry, Daniel. I didn't see that. Yes, you were right. 22577, exactly. Yeah, I don't know what they did here. It used to be that when I got a chat message, it would flash orange for a few seconds. It doesn't seem to do that anymore. So I'll keep my eye open for the chat room. In fact, I'll move it over here. All right, now this one's interesting. Now, clearly, 17 is a prime number whose only factors are 1 and 17. Since 1 is not a prime number, the only prime factor of 17 is 17. So this is a bizarre case where you only have the one prime factor. Remember, we said that 1 is not prime. But this number only has two factors, 1 and 17. And since 1 is not prime, that means that this is one of those oddball cases where the number only has one prime factor, which is itself. Okay, so whenever you have a prime number, this is exactly what will happen. Okay. All right. Greatest common factors. Now remember how we set this one up. You're basically just looking for multiples. And the thing is, it's hard to tell how far you have to go. You can basically try a few. See, now in this case, we got lucky. We can see right off the bat that 18. Oh, wait a minute. I'm sorry. I'm doing the wrong thing. This is least common multiples. My fault. Sorry. I got you off to the wrong track. Yes, that's coming next. Sorry. No, this is greatest common factor. Well, it is Monday morning, isn't it? Yeah, so no, sorry. This is the one where we do this. We break it up into factors. We have the binary trees. Now, this one can be broken up into 1 and 3, but remember what we're looking for. So for 3, there's only one prime factor, which is 3. Over here, the prime factors are 3 and 3. What we're aiming for is to find what they have in common. They only have the 1, so therefore 3 is the greatest common factor of 3 and 9. Yes, and sometimes that happens, and one of the two numbers is the greatest common factor, and that's certainly what happened here. Okay. Now 10 and 35. Let's see what's going on there. 10 can be broken down into 2 and 5. 35 is just 5 and 7. So the prime factors are 2 and 5. So what do they have in common? A 5. 5 is the greatest common factor of 10 and 35. Man, somebody is doing very well today with those greatest common factors. Very good. How about 7 and 10? Now, this is a bit of a trick question because, well, 7 is a prime number. 10 is not. But the bottom line is the prime factors are 7 over here, 2 and 5. They have none in common, do they? They do not. So this is another strange case. Since 7 and 10 have no common prime factors, we say that the greatest common factor of 7 and 10 is 1. Okay, in other words, we will define this case to be 1. Now, remember, it does say greatest common factor. It doesn't say greatest prime factor. So 1 is a factor, not a prime factor, but it is common to both, and is the only factor common to both. So therefore, we will call this common factor 1 because they have nothing else in common. So in other words, it's one of those, again, a strange case where when something unusual like this happens, we're going to just say 1 is the greatest common factor. That happens in math sometimes. You run into oddball cases and you have to decide what to do. And here that something is to simply say they have a greatest common factor 1. Now, here's another case just like that. Because if you look at these, oh boy, they don't seem to have, oh wait, what did I do? Sorry. Let's call this 2 and 3, not 6 and 1. And guess what? They have nothing in common. So the prime factors are 2 and 3, 11. So therefore, the greatest common factor equals 1. because they have no prime factors of any kind in common. And it happens, you know, not all numbers have common factors. It doesn't always work out that way. All right, now we're going to do the least common multiples. I accidentally started to do this before. So for 5, we have 5, 10, 15, 20, 25, 30, etc. For 10, we have 10, 20, 30. And what do you know? The smallest common factor, a common multiple is 10. All right, so they both share a multiple of 10. That's the smallest one. They also have a common multiple of 20 and 30 and 40, etc. But we're looking for the smallest one. So the least common multiple of 5 and 10 is 10. And sometimes that happens. Sometimes the least common multiple of two numbers is one of the numbers. All right. How about 12 and 24? For 12, we have 12, 24, 36, 48, 60. For 24, we have 24, 48, 72. So again, you see they do have more than one common multiple, but the one we care about is the smallest one, which is 24. And once again, it proved to be one of the two numbers. That's always a possibility. Now, how about 5 and 7? Okay, this one might be a little tricky. So let's look at these carefully. And let's see where they have, here we go. 35. And this time, it wasn't one of the two numbers, it was actually the product of the two. So the product of the two numbers is guaranteed to be a multiple of both of them. It isn't necessarily the least common multiple, but it is always a common multiple. And so if you can't find one, this might be your answer. Okay, so just remember, the product of the two is itself a multiple of both. It could be your answer. And this time it was. Okay. Now we got 6 and 10. Now this one looks a little challenging. Well, let's see. And I think I mentioned once before, some people, once somebody in the class showed me a technique they were showing in high school, and I'd never seen it before, for doing these least common multiples. And I can't remember anything about it anymore, but if somebody showed you a quicker way of doing this, you can feel free to use it. I'm not sure if such a thing exists, if a quicker way exists, but if it does, go right ahead and use it. Your calculator isn't going to be able to do this. It's not set up for that kind of thing. But you never know what you're going to find in a calculator. So anyway, let's look at these multiples. Oops. Uh-oh, what did I do? 6, 12, 18, 24, 30. No, that's right. Okay, and then 10. Oh, I think we have a winner. It looks to me like 30 is the least common multiple. Okay. All right, so it happened to be 30 this time. All right, now we've got two word problems coming up. Now, every time when I'm in the classroom with this class, whenever I say the word problem or the phrase word problem, I always get at least a few people who actually, I would say, react like they've seen a ghost, let's say, or something equally scary, because they just don't like word problems. And I don't know what the exact problem is. Maybe they've had some bad experiences with it or something, but let's just say that the reactions are not usually positive when I say word problems. So anyway, the challenge to word problems is to figure out exactly what we're being asked to do. And then when you see that, you'll realize it's just exactly like one of the other questions that we already did. Like here, for example, we have two people are bicycling on a circular trail. Not unlike the one we have at Purchase. You know, if you drive around that big loop, it is kind of a circle. I think it's more like an oval, but still, you get the idea. Actually, let me move this down here. So you can easily imagine if you pick any point on that loop and started riding your bike, eventually you'd be back at the starting point, wouldn't you? I mean, unless you get lost or something, but I mean, it's like this, okay? You start here, you go all the way around, and you come back. And it doesn't matter if it's clockwise or counterclockwise, but let's say we have two people who are bicycling, and they come and they start at the same point. The first person is fast, and they can get around the whole thing in 24 minutes. Let's call that person A. The next person is not quite so fast. All right, they're out of shape. They haven't done this in a while. It's going to take them 36 minutes to get around the track. So if they start together here, imagine them making the following agreement. Okay, we'll start riding. Now, obviously, A is going to get ahead of B very quickly. So they agree that when they meet up again, they'll have lunch. Okay. So when is that going to happen? Oh, now you've seen problems like this before. It sounds like it's impossible, but when you stop and think about it, why don't we do this? For Mr. A, let's draw up a list of all the times that he'll be back at the starting point in 24 minutes, in 48 minutes, in 72 minutes, in 96 minutes, 120 minutes. And let's say this is Miss B, and she'll be back in the beginning in 36 minutes, in 72 minutes, in 108 minutes. Wait a minute, what happened? Both of them will be back at the beginning in 72 minutes. Now, by that time, Mr. A will have gone around the track 3 times and Miss B will have gone around twice. But the point of it is that they'll both be back at the starting point in 72 minutes, and then they can have lunch. So what have we done here? It turns out that this scary looking word problem is nothing but a least common multiple problem. And once you recognize that, it becomes easy, doesn't it? See, so that's the challenge, recognizing that this is nothing but a least common multiple problem. Okay, so that starts you thinking, man, maybe when I see this again on a test, I won't have a problem with it because I get the idea. That means we're starting to get good at this stuff. Okay, when you start being able to use your creativity to understand and think about problems, solutions to problems, that's when you're starting to get good at it. Okay, this is when it starts to mean something to you, and you'll realize eventually that you're using this for other applications too. Now, with that all being said, let's look at 24. This time we're looking at lighthouses. We've got 4 lighthouses. The first one, and they're standing there on the shore, right, here's the first one with a big beam going out. And then here's the second one. And the third one, and the fourth one. What's separating them, and then, by the way, I mean, there are certain areas, like in Cape Cod, there is a stretch of beach where they had, at one point in time, there were actually 3 of them. And the reason why they need 3 is because you want to be able to tell. They're not all at the same spot, though. They're up, placed in different locations. They're trying to help you avoid certain, like, rocky areas, let's say, where this way you can tell them apart. They might have different colors. So in other words, the whole point of all this was to make sure you don't crash your ship because it's dark and stormy out. So in this case, we're going to assume that the first flashlight, and they start at the same time. The first flashlight, which we'll call flashlight, lighthouse 1, goes off every 10 seconds. So let's write a list of how often the first lighthouse will flash. Lighthouse 2 has been set to go off every 15 seconds. Now, again, this is done on purpose so that the sailors can tell them apart. Although in practice, they would also have different colors and other ways of separating them, but still, the patterns are also giving us useful information. Number 3 is going off every 20 seconds. And then finally, lighthouse number 4 is going off every 30 seconds. So what are we looking for? We want to know, if they start at the same time, how often will they flash again at the same time? Well, let's see. Okay. Looks like they all will flash in 60 seconds. No matter how many times they flash, all of them will flash in 60 seconds. It will not happen sooner than that. So the least common multiple of these lighthouses is 60 seconds. They will all flash together every 60 seconds. But there will be more, of course, but you can count on that. So every 60 seconds, you know, they're all going off at once. Okay. Now, obviously, this was much more important when we didn't have such sophisticated navigational equipment on the ships and, you know, satellite positioning and all this and that, sonar and radar. You know, let's say this is now not 2021, but 1821, and you're a fisherman coming in from a hard day's work catching cod off the coast of Wellfleet. You need this information to keep yourself from crashing on the shore. All right, well, anyway, but the bottom line is this is a least common multiple problem. And so this dreadful word problem suddenly became a very simple least common multiple problem. All right, so what if for some oddball reason today was a secret test? Let's say I suddenly said, hey, everyone, I've decided to have a secret test. This counts. How would you have done? Not that I would ever do something like that, but what if I had just said, you know what, take out a piece of paper and start working on this stuff. It counts. How would you have done? I bet you would have done pretty well. Am I imagining things? All right, but if you miss something, if you're not sure, you'll have plenty of opportunities to go through this at home, read through the solutions, make sure you understand them all. And if not, we'll discuss it next time. We'll go through it, or you can send me an email. If you're happy with this, then what you should do is work on the second problem set for Thursday, which, let me just show you what that's all about. And keep in mind that by working on these problems, you're also, in effect, studying for the first midterm, because this is what it's going to look like. Yes, so, oh yes, rational and irrational, simplifying radicals, simplifying expressions with radicals. Oh, this will be a fun one. By the way, oh no, this one, it's okay, it's fine. Yeah, this is good. Yep, all about radicals. Okay, so Thursday will be a fun day for radicals. But in the meantime, we're going to go back to chapter 5C specifically, and we're going to introduce something called arithmetic and geometric sequences. Now, we mentioned the Fibonacci sequence. That was a very complex sequence, but it was nothing but a list of numbers. All right, and in fact, let me go, let's see, is that in this section? No, I think that was in B, I believe. Towards the very end of this, I used it to introduce the golden ratio, I believe. There it is. This is a sequence too, but this is much more complex than the ones we'll be looking at. But just notice it is nothing but a string of numbers. And the idea here is that there's a pattern of some kind. And the pattern goes on forever. You can tell by these 3 dots at the end. Once you recognize the pattern, you should be able to fill in as many as you need. And sometimes these sequences can be reduced to a formula, which is very nice. We're going to look at a couple of simpler types of sequences here. And they're called arithmetic, as you can plainly see, and geometric sequences. So we'll start with the most basic type of sequence, the arithmetic sequence. And again, it's a list of numbers. Each number is referred to as a term. And I think you can tell by looking at this sequence what's going to come next. So who wants to predict what number would come next? Nobody wants to take a guess? What comes after 1, 2, 3, 4, 5, 6? Is it 70 million? No. Is it minus 54? No. Well, it's 7, and then 8, and then 9, and then 10, and it goes on forever. In other words, these are simply the natural numbers. Okay, it's a sequence. I could describe the sequence with a formula. And it does go on forever, but the pattern never changes. And what's important here is that the way I go from one number to the next is to add 1 to the previous number. Okay, in other words, to get from 2 to 3, I add 1. To go from 3 to 4, I add 1, et cetera, et cetera. And so any sequence in which I'm adding a constant to each term is called an arithmetic sequence. All right, arithmetic. So we'll start with that one. Geometrics are more complicated. We'll save those for later. So we'll start by noting that an arithmetic sequence is one in which the differences between the terms are constant. So here's some quick and simple examples. Like in the first case, this is pretty much the one we just did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the common difference between those terms? It's 1, okay? Because if you look at it carefully, 2 minus 1, let's all right, what's going on here? All of a sudden, my tablet refuses to work. Well, there it goes for some reason. All right. So here you've got 2 minus 1 is 1. 3 minus 2 is 1. 4 minus 3 is 1. Okay, so the common difference, we'll call it D, is 1. What about here? What's separating these terms? D equals 3. All right, and by the way, if you notice, the sequence doesn't have to start at 1. It can, but it
Professor,
doesn't. Yes, go ahead.
it's still showing the lighthouse problem.
It is. Oh, that's weird. That usually means there's something wrong with the internet. I'm glad you told me. I had no idea. I was like, what's going on? Nobody's paying attention anymore. So, all right. Well, that is very scary. Oh my God. This is what I mean about technology. Can you ever really depend on it? No. You should never depend on it. Always have a backup plan. Like just yesterday, I went to a store, and the credit card machines they have now are getting just a little too out of control, in my opinion. They're like, some of them you're supposed to tap your card, and sometimes you're supposed to swipe it, and sometimes you're supposed to make it read the chip. Usually the net effect is that none of those techniques work at all. So I ended up having to pay for something with cash because the machine refused to work. It wouldn't tap, it wouldn't swipe, and it wouldn't slide. And there's nothing wrong with my card. So, I was just saying, listen, this is what technology is. It works a lot of the time, but I would never, ever depend on it. And this is a classic example of what I mean. You figure that's something we should not have to worry about. Is it still stuck? Is anyone seeing my slides? There's one possibility. I'm going to turn off the sharing and turn it back on. Oh, for God's sake.